and here are a couple of work solutions for those specific heat capacity questions from the National 5 Properties of Matter booklet that I have linked in the description below. So we will be working on specific heat capacity. I'm going to start with some very standard questions and then do a couple of tougher examples. I'm going to be taking the questions from my phone, so excuse me if now and again I have to go and wake it back up again. So let's just do number 1 to get us into the swing of things. This is number 1 from page 3. How much heat energy, so EH equals question mark joules, is required to raise the temperature of a mass of 0.40 kilograms of copper from 20 degrees C to 100 degrees C. So my delta T there is 100 minus 20, 80 degrees. And they've told me it's copper, and what they're really telling me there is to go and look up the specific heat capacity of copper, which is 386 joules per kilogram degrees C. Okay, so there I have everything I need. I'm going to, over on the right hand side here, put my equation. E equals Cm delta T. Pop in the stuff I know. 386 times 0.40 times 80. And pop that into my calculator. 386 times 0.4, 80 is 12,352. Now that's too many significant figures for any answer. That is 1, 2, 3, 4, 5 sig figs. We should only ever put a maximum of 3 significant figures into our answer. So this one's quite easy to pop into scientific notation, which is what we should do as soon as the sig figs are too high. So 1.24 times 10 to the 4 there, joules. However, there is a button on your calculator that will do it for you, okay, and there it's done it as 12.4 times 10 to the 3. That's absolutely fine. There's nothing to say in scientific notation. You have to only have a single digit before the decimal point, so it's absolutely fine in science to have as many as you want. You could even write it as 124 times 10 to the 2 if you wanted. Okay, there is that answer. Let's try one where we do a little bit of rearranging now. So let's do number 3. What temperature rise, so delta T equals question mark degrees C, will result if 6 times 10 to the 4 joules, heat energy is 6 times 10 to the 4 joules, is supplied to a lump of iron, now I can go and look that up in just a second, of mass 0.20 kilograms. I just scroll up to my data sheet. Specific heat capacity of iron is 480 joules per kilogram degrees C. And you can just take that unit from the top of the table there. All right, over to my formula. We always write the formula just as it looks in the formula sheet. 480 times 0.2 times delta T, which I do not know yet, and over here I have 6 times 10 to the 4. Okay, so there's a couple of ways you can go forward here, folks. I can make life easier for myself if I want by multiplying these two together, so I have only a single number on this side. I'm not going to do that step at the moment. I'm going to actually take this whole thing down. So rather than putting them together now, I'm going to pop them together all in a oneer in my calculator. So I want delta T. Delta T is currently times by 0.2 and times by 480. So I'm going to divide by 480 and by 0.2, doing the opposite on the opposite side. Okay, and that whole thing is what's going to go into my calculator, using my fraction button to make my calculator screen look exactly like my page. 625 degrees C. It's a pretty big temperature change there. Okay. One more of these more standard questions. Let's do number 4. When a mass of 0.5 kilograms, m equals 0.50 kilograms. Notice, guys, I'm not reading the entire question in one go at first. I'm not overwhelming myself. I'm just putting the information down as it comes to me. Of material X at 20 degrees, okay, so I don't have a temperature change yet, is supplied with heat energy, 6 times 10 to the 4 joules again. Just check that is the same, yep. Its temperature rises to 55. There we go. Delta T is 55 minus 20, a change of 35 degrees. Calculate the specific heat capacity. And then suggest what kind of material it is. All right. EH equals Cm delta T. Same every time. Numbers in. 6 times 10 to the 4 is equal to C, which we don't know, times 0.5 times 35. So I want C. C is currently times by 0.5 and times by 35. So I'm going to divide by both of those things. 6 times 10 to the 4 stays exactly where it is. 0.5 and 35 come over to the other side, leaving C on its own. Fraction button. Okay, so I've got a C in the thousands here. My C values tend to be quoted to all of their numbers, but I am going to quote it again to just 3 sig figs. So this is 3,430. If I round that off, that 8 makes that 2 go up to a 3. Joules per kilogram degrees C. There we go. So with a number in the thousands like that, this is A, I'm thinking about B. If we go and look at our data table and the specific heat capacity of different materials, we notice that only the liquids, ooh, that's my light. We notice that only the liquids are really up in the thousands. The solids tend to be in the hundreds. So that means with this specific heat capacity, we are likely to be a liquid. Likely to be liquid with a specific heat capacity. This high. There we go. Okay, so now we're going to do questions 6 and 7, which are a little bit more conceptual and deep thinking rather than just kind of plugging numbers into the calculation. And then we're going to go over to an exam style example. So number 6 is no calculation in it at all. It is just a kind of a scenario that they want you to think about. So in number 6, 2 beakers contain the same quantity of water, but in one the water temperature is 10 degrees and in the other it is 30 degrees. The room temperature is 20 degrees. 2 water samples are mixed in an insulated container and the temperature is measured quickly. Predict, no calculations required, the temperature of the mixture immediately after mixing. So you just go with the most obvious answer here, guys. If you're mixing a volume of 10 degrees with exactly the same volume of 30 degrees, the final temperature is going to be right in the middle, 20 degrees C. By using an energy argument, justify your answer. So all heat energy emitted or lost by 30-degree water is absorbed by 10 degrees C water until, and this is a really important point, they are the same temperature. I'm shorthanding there, don't do that in tests. C, what difference, if any, would there be to the final temperature if an insulated container were not used for the mixture? Now, this is an interesting question. So usually, the final temperature would be lower because this 20 degree water would now immediately start losing energy to its surroundings. But the surroundings are the same temperature here. The room temperature is 20 degrees. So here, there would be no change to the final temperature as the surroundings are also 20 degrees C. So heat will not be lost. If the surroundings were colder, the water would immediately start losing heat energy to those surroundings if the insulation was taken away, and the final temperature would be colder. If the surroundings were warmer, the opposite would happen. But here the surroundings are 20 degrees, so although there will be heat energy being exchanged, it'll be kind of equal in both ways. It's totally random, it'll be a bit random, equal both ways, and they'll keep each other basically the same temperature. D, how would the final temperature measured just after mixing be affected if there were more hot water than cold? So again, obvious answer is the right one. If there was more hot water, the final temp would be warmer. And I'm going to add something here that I don't think they've really asked for in the question, but as long as there is insulation. Because, of course, adding a higher volume of the 30 degrees is going to put the equilibrium temperature above 20 degrees. So now, if there's no insulation, we will lose heat energy to the surroundings, and we would come back to the 20 degrees final temperature, because that's the temperature of the surroundings. Every inanimate object will become room temperature given enough time. It will keep exchanging heat energy with its surroundings until everything is in equilibrium. The only things that don't do that are living things that produce their own temperature through energy producing reactions, and objects that, other energy sources, so fire and electrical heaters and things like that. So things where we're actively transferring energy into heat energy. But inanimate objects that are not doing that will always become room temperature given long enough, unless they're insulated. E, explain why in practice the temperature of the surroundings is important in any heat experiment like this one. So, I've just explained that. The final temperature will always become the room temperature after some time. So the water will continue to lose heat to the surroundings if they are a lower temperature. Okay, so there was our concept question. And finally, guys, well, not finally, we'll have one more after this. We're going to do number 7. Number 7 is a really classic CM Delta T question. We haven't seen one like this in exams for a few years. It was really common back in the standard grade days. relatively common in it too, not so much in National 5, but this would kind of be your kind of A standard level of understanding for CM Delta T. So if you can do number 7, then you're doing pretty well. If you haven't attempted it yet and you want to see if your skills are there, then please pause this video now and go and have a go at number 7 before I give the game away. Okay? It's all very well hearing a teacher talk through it, but you really want to know, to really assess whether you can do it, you need to do it for yourself first. A blacksmith takes a hot horseshoe straight from his furnace and submerges it in a barrel of water. The temperature of the water rises from 14 to 17 degrees. Okay, so guys, I've got 2 different materials here. So I'm going to set, first of all, 2 different lists. That's supposed to say horseshoe. So the water goes from 14.5 to 17.5. Oh no, 14 degrees to 17.5. So that's a 3.5 degrees C change of temperature there. It's a mass of 25 kilograms. And the mass of the horseshoe is 1.5 kilograms. Okay, now you might think that's all we know here, but of course we don't. We know these 2 materials. So we know the water, we can go and look up its specific heat capacity, which is 4180, and we know that this is iron. So we know it's got a specific heat capacity of 480. Okay, and yeah. I'm going to question myself now, so I have to go and look at those numbers, even though I know they're right. There we go, yeah. So that's what we start off with. We clearly have enough information here to do a calculation about water. We do not yet quite have enough for the horseshoe. So let's see what they want first. Write down a statement involving the conservation of heat energy in this situation. Now, pupils often find questions like that really tough, okay, because we're just not sure what they mean. So when they say a statement involving energy conservation, all they mean is energy lost by one thing is gained by the other. So here we're going to say the heat energy lost by the horseshoe will be gained by the water. That's all they mean, just an exchange. Calculate the heat energy gained by the water. Okay, can do. Don't need to write down my information again, I've got a list just there. 4180 times the 25 kilos times 3.5 degree temperature change. I don't know if anyone's ever seen this process of dunking a hot horseshoe into water. I have a horse, so I see it relatively often, and it is awesome. So there we go. There's our. I'm just going to bring my light a little closer. There you go. You can see that better now. If my light would stay where I want it to be. There we go. There. So again, as usual with energy numbers, we have big high numbers. We've got to make sure we use just 3 sig figs. So I'm going to write that down as 366 times 10 to the 3 joules. Okay, and there's my heat energy of water. Don't ever worry about carrying when they ask you to use. Oh, my light is being really frustrating today. Don't ever worry when they ask you when you have to round a number and then you're going to have to use that number again in the future. They expect you to use the rounded number. All those significant figures are not really part of our answer because we didn't have that many sig figs to start with. So this is our final answer, and if we have to use it in the future, this is the rounded one that we use. Okay, I'm just going to go across to try and save space here. What is the final temperature of the horseshoe? Now, this is the kind of A standard question. So first of all, we do our calculation to find the temperature change of the horseshoe. Okay, so our temperature change is question mark. And you might be thinking, I still don't have enough information for that, but you do. Because of that conservation of energy, the energy gained by the water is the energy lost by the horseshoe. So Cm delta T, that's 366 times 10 to the 3 joules lost by the horseshoe for its 480 specific heat capacity 1.5 kilo mass times delta T. I want delta T. Currently it's timed by 1.5 and 480, so I'm going to divide by those two on the other side. Times 10 to the 3 over 480 times 1.5 equals delta T. So the temperature change of the horseshoe, 366 times 10 to the 3 over 480 times 1.5 is 508 degrees C. Okay, but that was the temperature change. That's what it dropped by. Now here's the really tough part. If the final temperature of the water is 17.5 degrees, then that means the horseshoe has stopped changing temperature as well, if that's the final overall temperature. So the horseshoe will also be 17.5 degrees. So if it dropped by 508 degrees and it ends up 17.5, its initial temperature must have been 508 plus the 17.5 it ends up at. Okay, so 508 plus the 17.5, I'm not doing it in my head, sorry, 526 degrees C to 3 sig figs. Okay. And there we go. So there is questions 6 and 7. They're definitely more exam style thinking. Calculate the final temperature of the horseshoe when it was removed. What is the final temperature? Oh, sorry. I've just realised what I've done. I've done D instead of C because I knew what was coming. So C, this is D. Sorry. C, what is the final temperature of the horseshoe? That is just 17.5 degrees. Sorry if I've just really confused you. So the final temperature of the horseshoe is 17.5 because the final temperature of the water is 17.5. So if it's a final temperature, it means they've stopped exchanging heat energy, which means they must be the same temperature. Calculate the temperature of the horseshoe when it was removed from the furnace. So there's the starting temperature of the horseshoe when it was popped into the water. Part E, explain why in practice such a situation would give rise to a smaller increase in temperature of the water in the barrel. I'm just going to squeeze this in here. So this is the same answer that you would always give. They're always going to ask this style of question, and that is because heat is lost to the surroundings. So of course, not all of that 508 degrees temperature change from the horseshoe would have been delivered to the water. Some of it would be lost to the bucket, some of it would be lost to the air. Okay, so the reason why we don't get quite such a perfect temperature exchange or heat exchange, sorry, is because heat is lost to the surroundings. They're always looking for that phrase. It's your stock phrase. So our final question we're going to do today is the worked example, which will also be in the description for this video. And it is really kind of exam style. It's got a graph to read things from, and it's got a bunch of different kind of calculations that come from slightly separate parts of the course. And it refers to an experiment. So it's really exam styly, particularly National 5. Okay. Here we go. 1 kilogram of paraffin wax, C equals 1 kilogram. Oh, M equals 1 kilogram, honestly. Is heated using a 300 watt heater. Okay, now that's a piece of power information. I know that does not go into Cm delta T. I'm just going to pop it over here, because I know that those two pieces of data don't go together. A graph of the temperature of the wax against time is plotted. The amount of energy supplied by the heater in 200 seconds. That's what the first thing they wanted us to calculate. Okay, can do. Power equals energy over time. So that's 300 equals energy over 200. 300 times 200 equals energy. Energy equals 3 times 2 is 6 with 4 zeros. Now, because I'm so terrible at mental arithmetic, I'm just going to check myself. I know I'm correct. I just, we all have insecurities, folks, and mental arithmetic is definitely one of mine. So, there we go. Now, what that means, guys, if the energy in the heater supplied that, then we are going to assume that that is the energy that the paraffin wax absorbed. So we can pop that down as our energy. Oh, there's like 6 times 10 to the 4 again. Goodness me. The specific heat capacity of the paraffin wax is the next thing they would like us to find. Okay, now this is where our graph comes in, because our graph is going to tell us our temperature change. So I've kind of squeezed in this little info this, haven't I? So we start at 10 degrees on our graph, okay, and in the 200 seconds we go up to 30 degrees. So our change in temperature is 20 degrees C. Okay, so I'm just gonna squeeze it in here, equals C. I should have put this power calculation over there. Cm delta T. We have 6 times 10 to the 4. C is what we don't know, times 1 times 20. 6 times 10 to the 4 over 20. I don't think we need to bother bringing that 1. Is equal to C. C equals 3,000. 3 times 10 to the 3 joules per kilogram degrees C. Seems right to me, nice round number. And part C, the time taken by the heater to heat the paraffin wax from 32 degrees to its 55 degrees C. Okay, so now they're wanting us to go back the way. So they're telling us that there is a change in temperature here of 30 to 55. So that is a change in temperature of 25 degrees C. And they would like to know the time taken. Now, that's in a completely different formula. We still know that we have a power of 300 watts. We're going to need to find the energy it takes to do that temperature change and then go to our power energy time formula. Okay, so we now know that the C is 3,000. We know the mass is 1 kilogram, and we want to find the heat energy to do that temperature change. So that is 75,000, 75 times 10 to the 3 joules. Energy equals 75 times 10 to the 3 joules. Power equals energy over time. 300 equals 75 times 10 to the 3 over time. Now this is the rearranging that people often get a little bit stuck on. Because they try and do it in a oneer, like every other kind of rearranging. We're just going to do it in our steps so that we always know we're doing things right. So we want time. Right now, time is stuck underneath this fraction. So the first thing we're going to do is, instead of dividing by time on the right, we're going to times by time on the left. 300 times t leaves me 75 times 10 to the 3. So opposite on the opposite side. Now I've got 300 times t. I want t on its own. So instead of timesing by 300 on the left, I'll divide by 300 on the right. T equals 75 times 10 to the 3 over 300. And if you notice, guys, what's actually happened is they've just swapped, the t and the 300 have just swapped places. But it's important to know how to get there. And that gives you 250 seconds. There we go. Okay, folks, I hope that has taken us from not really being too sure how to use these CM delta T's to seeing all the way up to an exam style. It is a slightly harder formula than we've used before, so don't worry if it's just going to take you a little bit of practice to get there. The most important thing is to remember what that C means, okay? The energy taken to raise 1 kilogram of the material by 1 degrees C, and that you can always go and look it up in a data table. See you next time. Thanks, folks.